So here we have an enzyme, and enzymes are proteins, and how they fold up is based on the primary, secondary, tertiary, and quaternary structures and how their R groups interact with ionic bonds, disulfide bridges, nonpolar interactions, etc. And so how the R groups interact to fold this protein will determine the active site of the protein. So the active site is the actual part of the enzyme, and it's like a groove in the enzyme. So when we talk about enzymes, they are proteins that speed up chemical reactions within the body or within a cell. So when we talk about chemical reactions, the beginning parts, the reactants, when we use an enzyme, we actually call the reactants a substrate. And the substrate fits into the active site like a lock and key. But the enzyme will actually just like change shape a tiny bit, and that's called induced fit to like encourage the reaction to happen a little faster. And then you have a reaction, so maybe products are made, and those are your products. Now, factors that affect overall reaction rates, if you had a whole bunch of substrate available, well then it's faster, the active site, you could have the reaction happen much quicker. Or vice versa, you could just have a whole lot of enzymes. And the cool thing about enzymes is that the active site isn't changed during the reaction, and they can just be used over and over and over again. Now, there are some factors, though, that can affect enzyme function. So sometimes enzymes are going to need a little bit of help to get started, to be able to fit that substrate. So if I take this enzyme here, sometimes there's a molecule called a cofactor or a coenzyme. And co means to help or to work together, like co-worker or cooperation. And so this molecule is called a coenzyme if it's like a vitamin, or a cofactor if it's a mineral. And there's two ways that a cofactor or coenzyme can help. They may attach in that active site. Oh, it's this dark purple thing you can kind of see. And that will now create a shape, a more specific shape for that substrate. So now the substrate can come in and attach, and there's products. Now, cofactor or coenzyme could also attach allosterically. So if it comes off to the side and it changes the shape of the enzyme, so now that substrate can come in and attach and have the reaction happen. So regardless, cofactors and coenzymes, they help start the reaction. Oh, I can't see that. So cofactors and coenzymes are going to initiate or start the reaction, and they're required for that enzyme to function. Now, there's also something on the opposite of cofactors and coenzymes. So cofactors and coenzymes, while they help the enzyme, there's also things that block it. So let's take this enzyme, and if I have a substrate, sometimes the enzyme can be exposed to an inhibitor. So this pink thing is going to represent, we'll just move this lower, an inhibitor. Now, inhibitors can work in two ways. An inhibitor, if it fits competitive inhibitor, there you go. So if an inhibitor actually attaches to the active site, that will actually block the substrate. So now the substrate cannot come in for a reaction. So that is a competitive inhibitor. It is blocking or preventing the reaction from occurring. So we call that a competitive inhibitor because it's competing with the substrate for this active site. Now, another type of inhibitor, though, that also blocks is a non-competitive inhibitor. Non-competitive, I don't know, that's not right. A non-competitive inhibitor, is going to actually change the shape of the enzyme. So it's going to attach to an allosteric site So in a non-competitive inhibitor, this active site right now is a good shape for the substrate to attach and react. However, if an allosteric inhibitor or non-competitive attaches to the enzyme, it changes the enzyme shape, and now that substrate can no longer attach. So allosteric inhibitors change the shape of the enzyme, preventing the reaction. Now the cool thing about competitive and non-competitive inhibitors, so competitive and non-competitive, they both like stop or inhibit the reaction from occurring. One does it, the competitive inhibitor does it by blocking this active site, so it's competing with the substrate, versus the allosteric just changes the shape of the enzyme. But regardless, the substrate here cannot attach to the active site for the reaction. This right here, I want to point out, this non-competitive inhibitor is not the same. Is not the same as Denature. That's not the same. All this was it changed the shape. When we talk about denature, denature means that so this is a protein that was formed by the interactions of R groups and stuff. And if you talk about denature, that's when the molecule is exposed to too much heat and it begins to unravel. Or it was exposed to ions or like protons in the environment, or sodium or chloride salts in the environment, and it disrupted the bonds, and so the entire protein unravels and is denatured. So denature is implying like the whole protein loses its shape. It's not due to an inhibitor. Okay, I feel like I should say that again. So denature means for the entire protein to unravel and lose its shape, whereas in non-competitive inhibition, it just is an allosteric, like a conformational change. Now, an allosteric inhibitor, if it's like a temporary or reversible inhibition, the allosteric inhibitor can come off and this enzyme can go back and then continue to catalyze reactions. However, sometimes it is a permanent attachment, like cyanide attaches permanently, forever blocking that enzyme. So it just depends on the situation. In our bodies and in cells, there's actually positive examples of allosteric inhibition that we'll learn throughout the year. Sorry. So let's go ahead and use an example of, oh my gosh. What is it?
Mr. Yu, Mr. Patterson, Ms. Bergen, and Ms. Turner, please report to B235.
Okay, so now here you have an enzyme. Let's go ahead and talk about, use the example of inside the Krebs cycle and the oxidation of pyruvate. So in glycolysis, at the end of glycolysis in the cytoplasm, you made pyruvate. Pyruvate has 3 carbons. And then we're going to oxidize pyruvate, and we take off one of the carbons, and now there's 2. That's acetyl. So if you remember, a coenzyme, a helper. So this red molecule here represents coenzyme A. So here, this coenzyme is going to help to start the Krebs cycle. So what happens here is you have the acetyl-CoA comes in. Here's that 4-carbon molecule. Now an enzyme is going to attach them. So this coenzyme, you can think about it as helping the reaction to join, and then this coenzyme will actually leave, can be used again, and now we have citrate. I don't know if that was a helpful example or not, but hopefully this video was helpful for you in reviewing the vocabulary of enzymes.